Welcome to session 4 of Outsmarting contracts. We have been truly all around the world, looked at the most basic things from how MetaMask works, what an RPC is, what an injected Web3 provider is, how to write code from your web console, how to call different kinds of functions and think about some basic gotchas in Solidity from the early days. And then we explored Remix, the integrated development environment from the foundation. We played around with our own contracts. We've begun to think about complementary opposites as they exist in the technical worlds, where we learn how to have an intuition for the language of defense by writing adversarial contracts, seeing how those patterns play out based on historical hacks, and then sort of deriving safe and resilient and robust ways to write code as a result of looking at all of that kind of stuff. And we've reflected, I think, quite a bit also on this idea that the mere fact of Ethernaut's existence is kind of radically different from any other financial or economic paradigm that has ever existed before, right? Like, we're not out there to kind of hide all of the bad things that have gone on, but they're used as educational material, which is really interesting and something to kind of reflect upon if you're thinking about, again, like the long time horizons across which these networks will operate. And while it might be difficult still to grasp some of the lower level concepts, which we've begun to touch on in the past session, especially with this notion of storage slots and delegate calls and changing the states from within the context of a different contract, and some of these more convoluted and delightful things, the fact of the matter remains that in order to understand this stuff, you just have to be in these kinds of sessions and apply your mind. Whereas in order to understand the current financial system, you have to kind of look like me and have a certain kind of education and be part of the old boys club and legible in the network of mostly white, mostly educated Western men who have a certain perspective of the world, neither necessarily bad or good, just limited, as with all of us. And the great joy of these kinds of environments, if we are intentional about the way that we approach them and the way that we share knowledge and best practices, means that we can bring a diversity of perspective that informs the resilience of our code. And that's really exciting to me. So that's the one aspect. As I said before this recording started, the other aspect is of this guild. The intention beneath it has always been that we're here to kind of make mistakes together and look at what development actually looks like on a day-to-day basis, because it's not necessarily always the smooth and professional flow where you have this beautiful visionary idea of how you're going to write the next generation of economic code, and then you just implement it and it's like, whew, done. It's really often not the case that is the way things work. And prior to the session, I have been having some delightful problems trying to attack some of our smart contracts. So we will go through that together slowly and see where we end up. Thank you very much to Paolo on recording for sending the ETH that will power this session. I have to start doing, like sponsor calls at some stage of these, all of your kindness. And yes, where we will start today, because as you know, I'm not a very linear person and like kind of throwing curveballs in wherever I can. We'd got up to Vault in our previous session, and this was about sort of inspecting the storage of a contract, if you'll remember. And even though we declared this password as a private variable, we can still look into the slot that holds it, which in this case is slot 1. Slot 0 holds the Boolean about whether the contract is locked or not, and slot 1 holds the password. And we can go and inspect slot 1, get the password, pass it to the unlock function, and off we go. So declaring variables as private in Solidity does not make them private in the sense that you would ordinarily expect it coming out of some more traditional development context. It just means that a public getter function is not written for that particular variable. It doesn't mean that people can't inspect storage at that place in the contracts and see what is there. So I thought, rather than going directly into sort of re-entrancy and king, which will probably form the major part of this session, particularly if I can't crack them, in which case they will form the entirety of the session as we kind of sit awkwardly and look at our code and wonder why it doesn't work. I thought we would just start with privacy first, because it continues this particular theme of storage, but just in a slightly more complex way. So if you take a look at the description for this level, it says that as opposed to vaults, this contract has been careful enough to protect the sensitive areas of its storage, but we still need to try and unlock it to win, right? And so if you look here, we begin like we did in vaults with this Boolean of locked, and it's been set to true. But then we have a whole bunch of other stuff going on here, right? So it's not just a password stored in the next slot. There's a bunch of other things that we need to consider. And we need to know just a little bit more about how storage works in order to get access to the key that we need to unlock this particular contract. Now, it's actually fairly straightforward. The thing to be aware of in this particular example, I suppose, is these type declarations here. You can see uint8, uint8, and uint16. So these are slightly different to anything that we've seen before, because it's all been uint256s. You know, if you just declare a uint without putting any number of bits behind it, it defaults to 256. And so that's what we've been dealing with, these unsigned integers, which take up an entire storage slot, because each slot is 256 bits in your contract storage. But here we are declaring different types of unsigned integers, only 8 bits, 8 bits, and 16 bits. And this results in what we call variable packing in Solidity. So if you have a number of variables declared consecutively that don't fill up the entire 256-bit slot, Solidity will pack them into the same slot. Often when you're writing contracts, you'll see this kind of thing done because it optimizes storage and therefore optimizes gas costs, particularly when you're deploying your contract. When you store something in a contract, it uses something called the S-store opcode in the EVM, and each opcode in the EVM has a particular gas price. And the S-store opcode is one of the most expensive, because storing data on the chain is one of the most expensive communal actions that you can take, because blockchains have this really ridiculous structure in which all of the data is propagated to everyone all of the time. That is, you know, when you hear maxis talk about this kind of thing, it's decentralization, censorship resistance. It's so good. It's also incredibly inefficient and really stupid from an architectural perspective. There's a really wonderful post somewhere in the kernel syllabus called "Bitcoin is worse, is better." It was written in 2011 by a really wonderful internet blogger who was considering the fact that no cryptography expert would have ever designed Bitcoin, could have ever designed Bitcoin, because it's just so incredibly dumb to have all of the data propagated to all of the people all of the time. It's just not something that a purist, you know, either computer scientist or cryptographer would ever have done, but it's part of the genius. And because there is this architectural feature of how blockchains are put together, S stores on Ethereum are incredibly expensive. It also plugs into some of the other stuff that you'll find in kernel, where we talk about how freedom of speech, if you go back to module 2, the money and speech piece there, you know, freedom of speech on a blockchain is a very different concept, because you are free to speak however you want, as long as you pay the cost that we communally decide on in our consensus rules. S stores are a great example of that kind of thing. You're free to store whatever you want, but you pay for it. And you pay for it in a way that is provably more expensive to you than the community of listeners. And this is why it's so interesting that we can have these kind of discussions where we say we free meaning by pricing it correctly, because meaning has a very well-defined concept, which is any state-changing function. Anytime we sign a transaction in MetaMask, we're changing the shared state of the entire network. Hence, we have to pay for it. Hence, we can speak very clearly about what meaning is and look at the kinds of state transitions that it entails and price those state transitions effectively. So you don't have to have this kind of error handling like we do in the current setup, where we enshrine free speech as some kind of constitutional good and then sue people based on libel and defamation and use human interpretation in courts of law, which are premised on the threat of violence and the monopoly of violence that the nation states holds. We can do away with that entire structure of doing things and just have provably meaningful speech priced correctly in such a way that anybody can freely engage in it. Of course, that does raise the question of who can speak, given that there is this cost associated with it. But if you read that piece on money and speech, there is some thinking there about the creativity inherent in programmable money. That means that it need not necessarily devolve into oligopolies or rule by the richest, but the way that we program our money can in fact enhance the ability for anybody anywhere to speak, while maintaining this property that we don't try and protect free speech, which is what simultaneously pulls into being its manipulation. We just price it correctly. It's a much more beautiful and simple way of doing things. Anyway, all of that from variable packing in Solidity. And in order to attack this contract, we just have to understand that these three variables that are declared here, flattening, denomination, and awkwardness, are all packed into one slot. So the Boolean locked is in slot 0. Then because we have a 256 unsigned integer declared next, this will be put into slot 1. It can't go in slot 0. The Boolean doesn't take up the entire slot. But because this is a 256-bit unsigned integer, it will go on its own into slot 1. Then these three variables will all be packed into slot 2. And that means that the data that we're interested in here, which is a 32 bytes array of length 3, that's going to be in slots 3, 4, and 5. We can go through them and we'll take a look at each of the slots, but that's kind of what we're looking for. And then as we see here, the key that is needed to unlock this contract is the first 16 bytes of whatever data is at position 2 in that array. So that will be slot 5, right? Because arrays are 0 indexed, we have an array of length 3 that will, data of 0 will be at slot 3, data of 1 will be at slot 4, data of 2, which is what we're interested in, will be at slot 5. So we're going to have a look at that and see if we can get what we need in order to unlock this contract and speak in a way which might not have been meant, which is a whole other field of discussion, which we can open up in terms of, is code really law? What is the difference between spirit and letter? One of my favorite discussions, actually, spirit and letter. That's such an interesting way of thinking about things. You know, if you're any kind of legal eagle, what is the spirit of the law versus the letter of the law? Fascinating to kind of consider. And it speaks quite deeply to intentionality in law as well, which is a very well understood concept. Sometimes when we speak about intentionality, it can seem like it's this sort of seemingly abstract, somewhat spiritual concept, but it's not. Intention is the difference between manslaughter and first-degree murder in law, for instance. So anyway, we've got our instance. We've spoken a little bit about spirits and better while that's been happening. And as I say, what we can do here is if we just sort of await, it's web3.eth.get storage at, which is what we're interested in. And in order to do that, we need to first pass the contract address that we're trying to get the storage for, which is our instance. And I just want to go through each of these slots so that you don't have to believe me about what I've just said about each one being where it is. At slot 0, you can see our Boolean, right, which is initialized to 1, which is true. So that definitely checks out. If we look at slot 1, this is the block.timestamp, right? So whatever time is going on there, and it's 256. So you can see it's padded with all of these zeros to 256 bits. We can then look at slot 3. Slot 2. Let's take a look at that. And this will contain our flattening, denomination, and awkwardness variables, all sort of packed into this here, and then again padded to 256 bits, because the next thing is going to be our data array. And we're most interested, as I say, if you look into this, it's the piece of data at position 3 in the data array that we're most interested in, which will be at storage slot 5, because each of these pieces of the array are declared as bytes 32. So bytes 32 is 256 bits. So each one will occupy an entire storage slot. And that means that we can go and inspect storage slot 5. And this is the beginning of the key that we're interested in, right? But as you can see, it's declared as a bytes 32 and it fills up all 256 bits here. But we're actually only interested in the first 16. And that means that we have to figure out how to cast from bytes 32 to bytes 16. And there are some wonderful resources which will help you through this. I don't know if I have them loaded here. I don't. But all you need to know is that, like, when you cast unsigned integer from something bigger to something smaller, you lose the sort of the most significant bits, stuff on the left-hand side, all of this. And when you cast bytes from something bigger to something smaller, you lose all of the least significant bits. So all of this stuff here. And it's a fairly easy kind of manual calculation for this, because if we're going from bytes 32 to bytes 16, we just need, this data here is 64 base encoded. So we just need the first 32 letters and numbers, and that will be our byte 16 key, in addition to the 0x at first, because that's just there by convention in the EVM. So it's a little bit finicky, but if you grab the first 32 letters of this, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 25, 32, and copy that, then you should be able to just directly call the contract and its unlock method with those first 32 characters plus the 0x as a string. And that should unlock our contract. As I say, it's a state changing function. We're speaking meaningfully, and so we have to pay some kind of cost for it. Because if it is successful, it will change the storage associated with this contract and therefore the state of the network. We've successfully called that. It seems like we've probably been successful at a first glance at that transaction object. We can take a look just by inspecting the locked variable, because it's public. It is indeed set to false. So we've got it right. We've inspected the correct part of our storage, understood a fair bit about how Solidity packs variables in storage. It's important. That's an important note as well, that like Solidity will not, it doesn't pack variables in call data or memory. So like don't bother with that. It has no effect. It's only in actual storage where this variable packing takes place, just in case you're interested. And we have understood how to sort of cast between byte 16, from byte 32 to byte 16, which is just taking the most significant bits. For UInts, it's the opposite way around. Yeah, take the least significant bits. And that's because our locked variable is now set to false. We should be able to submit this instance and have Ethernauts cast rainbows throughout our terminal. And, give us strength and succor for the next two tutorials, which I've not been able to conquer yet. So we're going to try live and see if the demo gods are feeling like a reversal of fortune today, where everything doesn't work prior to it, but does. We'll see. There is my Nyan cats, my little beautiful rainbow array. We've done well. We've unlocked privacy. We've looked into storage where it needed to be, and that means that I kind of can't avoid it anymore. We're going to have a look at King and Re-Entrancy today, which are really the main parts of our session. And I am wondering, okay, we'll just try King. I've not been able to completely work it out, but I've made some changes and perhaps that will work. So we'll begin here and also then take a look at a similar but extended pattern in Re-Entrancy. So you can see that this contract represents like the ultimate Ponzi scheme, right? Someone is set as king, and there's a particular kind of value associated with that kingship. And if you send an amount to the king contract that is greater than the current king, it will send the value to the current king and you will become king. So this is the important part here. We have to break this game, and when we submit the instance back to the level, it's going to reclaim kingship. You will beat the level if you can avoid such a self-proclamation. So we have to become king of this level and then prevent anyone else from becoming king after us. That's basically what it's asking us to do. So let's take a look at the contract itself. We have the general sort of license identa and pragma Solidity compiler version specified, the contract keyword, these first three variable declarations. We have some address, which is set to the king, some unsigned integer, which is assumed to be 256 bits for the prize money, and then some address of the owner, which specifies the owner of this contract. The constructor will set the owner to whoever sends the message and will make them king, and it will set the prize to whatever the message value is. Then we have this fallback function. Remember, if it's not like declared as function something, but rather just a name, this is the fallback. It's external and payable, as you would expect with most fallback functions. It has a require statement first up, which says that the message value when you call this fallback function has to be greater than or equal to the prize, or the message sender has to be the owner, one of the two. And if that's the case, then this is the line which is kind of interesting for us, king.transfer, whatever the message value is. So this, if we can prevent this from being called, that will allow us to claim kingship and ensure that nobody else can do so too. And what I mean by that is, like, clearly we're going to have to write our own contract here again. And if we have sort of two options with this contract, right? Either we just don't implement a fallback function at all, which is the easiest way to do things. because if there's no fallback function in our contract, which will become king, then this transfer will fail, right? Because it will be, this contract will be trying to call our king contract and transfer from it. But if it doesn't implement a payable fallback function, then that will fail, and the Ethernaut level will not be able to reclaim ownership. The other thing that we can do, and what I want to try, just so that it's clearer what is actually going on, because otherwise, if you don't have some fallback function, you can just like win the level without really understanding what's going on, is like write a fallback function, but just make sure that it reverts. And then like it will get called once our contract becomes king, and it'll just revert. And that will mean that Ethernauts can't claim ownership, can't claim kingship of the level back from us. And then it resets king and prize, which you would expect. And there's this other kind of function, this other getter function here, which allows us to take a look at who the king is at any particular moment. So with much trepidation, let's get a new instance and see how far we can get with this. You can see here it's worth kind of just noting, because like we've kind of been a little bit lax in some of the previous guild sessions about just inspecting the details of our transaction. Like make sure you're aware of what is going on here, because I wasn't the first time. And I was looking at this and I was like, oh yeah, it'll be fine. I can test all of this stuff if I've just got one Rinkaby ETH left. And then I deployed this contract and paid 1 ETH when deploying it, and then was left without the ability to test anything. So we're clearly deploying this with a prize of 1 ETH. And it's always worth just having that as like a best practice whenever you're using MetaMask and interacting with anything. Like it's really deeply worth like stopping, breathing, maybe going and having some tea, like generally just having like some kind of routine in your mind that gets you to pause and like look at the transaction details and the data and the stuff that you're doing, because once it's signed, it's done. And I'm now a whole ETH pourer. Thanks, Ethernauts. Okay, but we have an instance, which is wonderful. And as I say, we want to try and write a contract which is going to claim kingship, and then not give it back, either by having no fallback function or by having a fallback function which just reverts. I think that we'll start with the fallback function that just reverts, so that it's clear what it is that we're actually doing. If I can close this, which I cannot. Okay, so we'll follow the usual structure of things in Remix. As you remember, we're in our top left-hand selection, which is our file directory, and we're going to create a new file called attackking.sol. You should be increasingly familiar with the structure of these. We begin with an SPDX license identifier. I've been using MIT the whole time. I kind of prefer GPL, to be honest. I've been like reading some of these licenses and thinking about them. Like the GNU general purpose license is kind of, it has a nicer history, personally. I think, it's written by Richard Stallman, who's also like a little bit crazy, but he's done like a really like incredible work at the Free Software Foundation, and has been an important figure in the history of open source. So that's also one that I kind of highly recommend, GPL. But we'll carry on using MIT for now. We have to sort of declare our pragma version of the Solidity compiler, which we'll say is anything above 0.8.0. I'm typing like a little bit of a nana today. And then, as I say, we just want to write a contract that is going to be able to send at least 1 ETH, because that's what's, if we send at least 1 ETH to this contract, and I'll show you how I know that it is indeed 1 ETH, that will claim kingship. It can just be exactly the same as the price because it's greater than or equal to there, and then have no fallback or a fallback which reverts. And just to make sure that I'm not lying to you and that it is indeed that the price is 1 ETH. You know, again, we can take a look at the storage, right? And we can get storage at, we have to pass it our contract address as per usual, which is a string. And then again, we're going to look at storage slot 1, right? Because the address of the king is in storage slot 0, and then this UN256 is the prize in storage slot 1. It should return some hexadecimal thing, and that's kind of interesting because we have to know how to translate that into decimal, which again, there are in the Web3 and the Ethers library, this big number sort of library that BN that you can use, bn.js, but that's no longer a part of what MetaMask injects into the site. So we can just grab that particular relevant parts, which is not padded to 256 bits. And I have preloaded hexadecimal to decimal converters, rapidtables.com. There's many of these online, and you can see that it comes with this really big number here. And if we count, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, which is kind of what we expect. This is 1 ETH, because what we're getting returned here is actually in Wei, and 1 ETH is 10 to the 18 Wei. So we've got 10 to the 18 there, which is 1 ETH. That's kind of what we're expecting. So we know that we have to send a message to the fallback function of this of at least 1 ETH that will make us king, transfer our message.value to the current king, and then make us king, reset the price to our message.value. And then if we ensure that there's no fallback in our contract, surely Ethernauts will not be able to claim kingship of the level back. Let's see if I can do this. We are going to follow the same convention, attack king. We will all, because we're not using an interface this time, we can just sort of declare our king address and set it equal to whatever our instance address is here, so that our attack contract knows where to target. We can declare our constructor, which is wonderful, and we can make sure that it's payable. We shouldn't need to do anything else with that. We'll just need to, we declare it as payable because we'll have to seed this contract with at least 1 ETH in order to send that ETH to our current king instance that we're trying to attack. And then let's write our, as per usual, pawn function. Again, we don't need to pass any parameters to it. So we do need to make sure that it's public. And what we can do here is we're trying to transfer whatever ETH is in this contract to the king contract. And generally speaking, and like the way that you might find it online, which is, I think, what was causing me to fail earlier. So we're going to try a different method here. There are like a number of ways that you can transfer ETH from your contract in Solidity. The 3 sort of most used ways over the years have been send, transfer, and now call. It used to be the send, you would return some Boolean. Transfer would revert if it wasn't successful. And so like transfer was implemented later. First we had send. And because it returns this Boolean, sometimes people wouldn't know about that Boolean being returned and would write buggy logic, which just expected it to be successful, and then things broke. So the Solidity team implemented transfer, which reverts on failed execution, and people have been using that. But ever since the Istanbul hard fork, this is a little bit problematic because send and transfer both specify a gas, specify a certain amount of gas to be used, which is 2,300, and Istanbul changed some of the opcodes and the price of them. because that's something that we can do, right? Like, again, when I speak about these opcodes like the S store and M loads and all of these different kinds of things that you can find in the Ethereum yellow paper, they're not immutable, right? They're in an open source public repository and are subject to change according to communal agreements. And Istanbul was this hard fork where like many of the opcodes were, the price for them was changed. And so like send and transfer have sometimes been failing because you're trying to do things with the specified gas limit of 2,300 and it doesn't succeed. So the way to send ETH these days is to use .call. And we can take a look at exactly what this does. I just want to write out the rest of it, which is that call expects some sort of JSON object. Well, it's not JSON, but like it's sort of written like that, where you can specify any number of things, in particular the value and the gas. Here we're going to specify, let me actually just, because it's better practice, I'm going to write a uint public amounts. I'm going to set it equal to 1 ether. And I'm going to transfer value of amounts over here. And then you have to actually sort of execute the call. And this might seem like a little bit of strange syntax. It's used for like essentially whatever data you're going to send in addition to this call. Let me see, I do indeed have an explanation of this, which I can share with you. And it should be here. Here is an explanation of like what happened with send and transfer. And I think that this is, yeah, here we go. We can take a look on the ever helpful Ethereum Stack Exchange to look at the difference between call and call with an extra bracket afterwards. The syntax has changed, as you'll see. It's no longer call dot value or call dot gas. It's what we're doing here, call with value specified in curly brackets, and then after it, that's second, generally speaking, empty, but sometimes with data in its execution parenthesis is how I kind of think about it. You will see that this is probably the clearest answer now. This particular link no longer works, but if you're calling some function, what essentially you're doing is like this kind of structure. It calls the modified function f and specifies the value with which to send it. And for instance, here, the data to be sent along as the payload, right? So you kind of have to have these extra brackets because that's what actually means, like, okay, execute this call, which is like an additional function on top of the function being called. And that's how we safely transfer ETH these days. A little bit complicated, but again, the result of the collective consciousness of many different people, many different hacks, and this constantly evolving expressive environment in which, for instance, at Istanbul, we figured out that like we actually have to change some of the opcodes and their pricing because the landscape in which this new order of econolinguistic expression is taking place has shifted, and we need to sort of update the costs of certain kinds of meaningful execution, which is really interesting in my perspective. Anyway, so I'm really going to hope that this that this works. We'll see. I'm not entirely sure. I can leave this as it is because that's what's going to sort of, it's going to execute an empty function, which is what will trigger the fallback. Now, this function, this contract as it is right now should work, right? It's like we could deploy it, and then when we call pawn, it would send, we would deploy it with 1 ether, call pawn, it would send that 1 ether to our king contract, that it would become owner. And when the king contracts, when Ethernauts tries to call this receive function again to reclaim kingship, this king.transfer should fail because there is no fallback in our contract, and that means that king.transfer will not work. Our instance of king will not be able to get our attack king instance to transfer any money. But just to make that very explicit, another thing that we can do is write an explicit fallback function, which is external payable. And in it, we can just put revert with some message, like, haha, you failed, kind of thing. That's, that this will, it's just, as I say, you don't need this fallback function. It's just me being very explicit about why it is that this actually works. And I say that without having got it to work for myself yet, but let's see. The first thing that we can do is compile it as per usual. We see that it does compile. There are a few little warnings, particularly about having this payable fallback function that is not implemented with having a receive ether function. This is some of the joys of working in Remix and with these kinds of tools, because they'll tell you all of the bad things that you're doing. We're using a low-level call and not sort of handling any return value that comes back from it. It's all terrible because I'm a naughty hacking dev and I don't necessarily do all of the best things all of the time. But seeing as it's compiled, we can have a go at deploying this. And as per usual, in the third tab down, we select our injected Web3 provider, which connects us to Rinkeby, is the right account. And we want to deploy this contract. We have to seed it with some ETH, and we want to deploy it with 1 ETH, right? So that it can transfer that amount to our king address. You can understand why my tests were failing earlier, because we needed the blesser Paolo to send us all of that tasty Rinkeby ETH to be able to do these things. Again, when I deploy this contract, there is the 1 ETH that I'm expecting, plus whatever gas fees to deploy the contract itself. That all kind of checks out. Let's confirm it. The other thing that I'll say while this is going on, the reason that I've only put value in here and not gas, for instance, is that it's not considered best practice to specify gas in your smart contracts, precisely because of what we've been talking about, that gas costs for particular kinds of calls can change at different forks in the network according to wide community consensus. So if you have a contract that specifies a particular amount of gas to be used for a given call, and then 10 years from now, the network forks and implements different costs for different kinds of opcodes, that contract can all of a sudden begin to fail, even though when you deployed it and when you were running it for the first 10 years, everything was hunky-dory. So generally speaking, it's good to try and avoid specifying gas in your contract. Sometimes it might be unavoidable, but it shouldn't be if you can help it. The only people that you'll probably see doing that are hackers. So we've now got our attack king contract deployed, and this is really the moment of truth. This transaction should send the ETH in our contract to king, claim ownership, and make sure that Ethernaut can't claim it back. We will see. As I say, amazing. It worked. Okay. So what we can take a look at here, let's just check our attack king contract address. It's F19 that begins with 6C878. So if we, in our contract here, await the contract underscore king method, oh dear. So that's not worked, because the king we can see is still the level address 5Cs. That's not good. Let's see what happens and see if we can identify the cause of this not doing what it should have. So we can see that there was an out of gas contract execution failed out of gas. Okay. That means after having just said, look, don't do this, I'm going to have a go at doing this, which means that we can specify a gas amount. You can see that it tried with 41,000 gas. So I'm going to put 400,000 gas in and see if that works, which means that I really have needed Paula's blessing. I can recompile the contract with this gas specified, and I'm going to redeploy it with another of his precious Rinkaby ETH set to 1. There's also like a way of, you could write a function here just to claim your ETH back, which would probably be good, and just sort of send to me and actually send to me address. So yeah, this is, I've just sort of written this so that like if I fail again, I can at least get my ETH out of the contract, which will allow me to continue with the next tutorial. But it's not liking that. Oh, it's okay. That's rather than doing the transfer, which I said was a terrible idea. Let's also just specify the call with gas. 300,000 should be more than enough. I think that should be fine. It's not showing that. Okay, I mean that should definitely work. That's just for the moment. Let's just be a little bit risky because it's Paolo's ETH and not mine. So I'm feeling lucky. We can see if this works. If we specify a gas limit, and hopefully that will pass this time. Let's hope for the best. If we specify that gas limits, deploy the contract again. If this doesn't work, then we're just going to move on and put our tail between our legs and claim kingship some other time, asynchronously in our Slack, rather than going through this. So we can see that our new contract has been deployed, and if we call pawn, let's see, maybe we'll be lucky this time having set the gas properly. Although, as I say, like this is not a very long-term sustainable solution, but it's wonderful for attacking contracts, because it's unlikely that you would have an attack contract deployed and active for years on end. The transaction has been successful. Let's call that again. No, okay. I will figure this out eventually and post the solution in our channel. Unfortunately, it seems like we've not been able to get this, and it's still an out of gas. So it's not about the yeah, I will figure out a solution to this. It's interesting to me that this gas limit is still that, even though I specified something higher. but it could also be this is in GWay. Yeah, I will look into this and post our solution eventually. Hopefully, at least, as I say, like the intention of these tutorials is to just try and illustrate how we think about this kind of stuff. And I'm certain that this is the right kind of pattern that we're expected to use to overcome this particular level, and that it's definitely this line which is the vulnerability in this contract that is going to allow us to claim kingship in a way which will never be passed on. But why exactly we're struggling a little bit with the gas is, in Afrikaans they say it's bo my vuurmakplek, which is a lovely phrase which translates directly to it's above the place where I make my fire, which means it's gone over my head. Which I often feel like when I get deeper into the realms of ethernauts and solidity. So we'll move on to Re-Entrancy, unless anybody else has some thoughts about King. Cool. I'll post the solution at some stage in Slack. Okay, Re-Entrancy. This is probably the most famous vulnerability in Solidity, right? This is the vulnerability at the heart of the Dow hack, which I'm sure I asked in the preparation for this week's session to go and read a little bit about the Dow hack, and it was Ethereum had just got going. There was all of this work on Swarm and Light clients, Whisper and Slockit, which was Ethereum embedded into Internet of Things devices, in particular smart locks, and you would just have to send a little bit of ether to your lock, and we were going to upend Airbnb and all of these kinds of things. People were very excited, and one of the core aspects of that time was, look, okay, it's wonderful, we can write these contracts and whatever, but we need some kind of means of organizing around them. And Vitalik and some other people like Dan Larimer had been speaking about this notion of distributed autonomous cooperatives, or myself and sort of more prominently a wonderful lady called Primavera de Philippi and some other people had worked on something called DCOs, which is decentralized collaborative organizations, which is a moniker that I still prefer. But anyway, we somehow landed up at this thing of DAOs, decentralized autonomous organizations, and Slockit leading the charge to deploy Ethereum on the entire Internet of Things. Also wrote the first Dow contract, and well before we had sort of mimetically formalized this concept of aping in, pretty much everybody in Ethereum at the time put a whole bunch of money into the Dow, and it came out at about $160 million worth of ETH at a time when ETH was, I think, just a couple of $100 or so. It was a significant portion of, it was more than 10% of the ETH in circulation at the time went into the Dow contract. And we were all, massively excited. Griff Green was kind of the community lead. And then a month later, someone started draining the Dow. And the means by which they did it was this Re-Entrancy attack. It demonstrated some of the difficulties of writing executable language in these public adversarial environments. And it's, I think, quite happily, if we look at it over a long enough time horizon, has kind of resulted in a lot more care, attention, and sort of the notion of moving slowly, because the stuff is not like writing, an API to get your startup going where you can move fast and break things. It's much more akin to writing space shuttle code, because once you deploy it, that's it. As 2 of Paolo's Rinkeby ETH can now attest to, which along with my own Rinkeby ETH are permanently locked. So sorry, no way to get them back. Funny when it's on Rinkeby, not so funny when it's $160 million in a live contract that represents more than 10% of the circulating supply, and therefore was a very severe security risk long-term to the health of the Ethereum network, which is why the decision was made to fork the network and roll back those transactions. Contentious indeed it was, and it brings us back to this notion of what is the difference between the spirit and the letter, because when we talk about code as law, we're concerned really with the letter only, and we miss a lot of the spirit, which is about the context, right? Like it's not just about straight execution, it's about intention. And intention is this somewhat inherently ambiguous thing. And given the long-term security risks, if somebody was sitting with more than 10% of the supply of Ethereum and could therefore do some potentially very damaging things, we rolled it back. Whereas, for instance, one of the other things that we've already looked at, which was force, which related to the parity wallet hack, which, in terms of like dollar value at the time was actually more than the Dow hack in dollar value, not in ETH terms, but in dollar value. And the network was not rolled back for that particular hack, even though nobody sort of benefited from it. Those funds never went to an attacker. They were just permanently locked. Oops, I killed it. It was done. But the reason that that we could never get to community consensus about rolling those particular transactions back was that it didn't present as severe an ecosystem threat in terms of the raw amounts of circulating ETH. And again, there was lots of different opinions and debates about that. And that parity wallet ultimately has led to Polkadot and the Kusama network, and Gav sort of working just on that. Whereas he played, a really big and important role in the development of Ethereum, and we wouldn't have what we have now without him. So all of this stuff goes along with the history of what we're looking at. This is, I suppose, the reason that I tell you these kinds of stories is just to sort of illustrate that there genuinely is a collective consciousness beneath each of these things that relates not just to the way that we write code now, but who writes it, how we write it, what happened with the people who began it, where forks have arisen, why that's the case, different ways of thinking, and indeed different ways of perceiving the world, different ways of perceiving reality itself, which sounds like a very big kind of an abstract statement, but again, like the possible set of perceptions of the real is infinite. And when we are looking at infinite design spaces, as we've been doing throughout this entire course, the thing which defines our starting points is intention. And this is why we focus so deeply on intention, because when you're clear about that intention, it has a deep effect on the nature of your perception. And you can see different perceptions of what reality is and ought to be if you go back and you look at these debates about the Dow hack and the parity wallet hack and various different things. They're, these really rather simple technical things of a self-destruct, or as we're going to look at now, the ordering in which we do accounting in our contracts. But this thing about intention is kind of sometimes only implicit in those debates. You really have to read between the lines to think about, like, how is this person perceiving the real? That's kind of interesting to consider. Anyway, re-entrance. As per usual, we have the safe math imports, which we're used to because we're using solidity at 0.6.0. Going to use safe math for any unsigned integer. And as we had in the token contract, we have this mapping of address keys to unsigned integers, which we call balances. So associate some number with an address, which is its balance. And then a fairly simple contract, right? There's this function to donate stuff to, and that will go and look into the balances mapping at the address that is passed in as a parameter, and it will add to it whatever value is sent with this call to donate. We have a public view function, view being, it doesn't change state, payable meaning that it does, along with the fact that it can receive ETH. So this balance of just goes and inspects the balances mapping of the address and returns whatever uint it finds there. And then we have this withdraw function. And the withdraw function, you send it some integer amount. The first thing that it does is it checks that the balances it checks in the balances mapping for whoever has sent this message, and made sure that the balances mapping of whoever sends the message is greater than or equal to the amounts that you're trying to withdraw. If that is the case, then it sets up this Boolean, which it calls result, and kind of anything that comes after it, just that little syntactical sugar in Solidity. And it uses this same pattern that we've been struggling with in King, where it dot calls the value being the amount that you pass in, and it sends that this dot call will send it whatever amount you pass into it back to you via your fallback function, right? For an externally owned account, that's just going to transfer the value to you. But if we have a contract here, then this is going to call our fallback function, right? Because the message.data is just empty. And that should give you pause for consideration. And if there is a result, we just make sure that the amount is kept as it is. And only then do we adjust the balances mapping of this particular message sender, and we subtract from that balances mapping whatever amount is put in it, right? And like logically, this makes sense, right? Like you can imagine sort of being the Slocket developers, or indeed many other people that have suffered re-entrance attacks. This makes sense, like you check that the person who is sending or trying to withdraw this amount does indeed have at least that amount available in the mapping that you maintain in your contract. If they do, send it to them, and then updates to reflect the fact that you sent it to them. That's how ordinary accounting would generally work, right? It's like you check that it's a valid transaction, execute the transaction, put in your double entry, and off you go, right? This is how accounting has worked since the Medicis. But it's a problem. And it's a problem particularly when the way in which you do things is via this fallback function. Because what I can do is I can write some malicious code into my fallback function that interrupts the execution of the logic here, that re-enters it at places where it's not supposed to be re-entered, and just continually ends up calling withdraw before the next line of logic is implemented. And the way that we now speak about this kind of stuff in smart contract development, particularly with Solidity, although it applies kind of equally to Viper and Yule and whatever, I mean, even like Rust-based languages on other blockchains, because of the nature of the medium in which we do our accounting has changed. And so like the easiest sort of way of thinking about this is we speak about checks, effects, interactions, right? What we've got here is a check, an interaction, and an effect. And what we want is a check, an effect, an interaction. So the check is any kind of validation, which is like this kind of thing, checking that the amount is less than or equal to whatever the balance that person has. Then the effect is this, and you put it next before you do any kind of interaction, call, send, transfer, whatever. And we call this optimistic accounting. Which personally I love. I think it's wonderful. I'm a creative and optimistic accountant. I hated accounting during school. My dad was an accountant. He worked at a bank all of his life. And he never got to be optimistic about it. So it kind of delights me that, in fact, the safest pattern for doing accounting in these new public adversarial environments where you don't actually need double entry. Some people speak about triple entry accounting, but like there's no longer any need for reconciliation. You know, that's not, it's just the medium is fundamentally different. I'm not sure that triple entry accounting truly captures that. But I really like this term of optimistic accounting. And what it means is that you do your validation, you specify the effect that it has, i.e. it's going to decrease the balances by the amount that is withdrawn, and then you send it. And that way you're not opening yourself up to these re-entrancy attacks. But of course, that's not what this contract is doing. So we're going to have a little bit of fun, and we're going to try and write a contract which does what was done to the Dow contract and was then subsequently argued on chain by the Dow hacker that code is law. You know, that's what the Dow advertised. It had it on its front page. Code is law. You can't stop us. And then the hacker was like, yeah, cool. I think it's very funny. But anyway, let's again create a new file in our contracts directory. We can call this attack re-entrancy.sol. We'll start again with our SPDX license identifier. Thank you, autocomplete. Yeah, let's declare our pragma as per usual. For the Solidity compiler version, we'll just keep using what we've got loaded, 0.8. Sorry about that. And we're going to go back to patterns that we've seen in previous contracts, because there are a few things that we're going to want to be able to do here, right? Which is first kind of donate, so that we initialize our balances mapping for our address, and then withdraw. So we're going to need an interface which specifies both of those functions. So we'll call it by convention re-entrancy. And as per usual, we'll go and grab these function declarations, make sure that they are external rather than public. And the two ones that we're interested in being able to call and attack are, as I say, donate and withdraw. We'll need both of them, and we'll need both of them to be external. So that's the interface that we'll need, because those are the functions that we're interested in. And we can now write our contract, which is attack re-entrancy. As per usual, we will begin by just like declaring our instance address and initializing it with the correct interface that we've just specified. So we'll call this re-entrancy address. We'll set it equal to our new instance here. Again, we're deploying it with 1 ETH, which is kind of a lot. It's just, I really am burning all of Paolo's ETH. Okay, we've still got 3. So let's hope for the best, Paolo. Who knows? I also wasn't able to test this before the session, so let's see if I can get it right on first attempt. There's our instance address, and we can put it in there, and we'll declare our interface re-entrancy, and we'll call it re-entrancy contract, which is equal to re-entrancy at our re-entrancy address. So that sets things up exactly as we need. Sorry, I'm also just going to put a units amount, 1 ether, because we'll need that too in a moment, I think. Now, as I say, what we're going to do is try and write a function that donates what we need to into our re-entrancy contract, and then calls withdraw in the same thing, and then writes a fallback function which has the code which will continually interrupt the execution of fallback of withdraw and continually withdraw whatever is in our re-entrancy contract until there's nothing left. So like we can write a function which like donates, initializes that mapping for us, immediately calls withdraw, which because of the way that this withdraw function is called will trigger this particular line here, which will in turn trigger our own fallback function. And if we can put some malicious code into our own fallback function, then we can continually just re-enter withdraw in the re-entrancy contract, and we should be good. So as per usual, we will construct a payable because we're going to need to seed this contract. I wonder, it doesn't need to be an ether. I don't think so. Yeah. Let's see that it's being necessary. And if GWay is, let's just do it with like, I don't think that I need to be as profligate with Paolo's ETH as I have been in King. And then we're going to want to write a function which donates and withdraws. So let's continue using our pawn thing. We'll make sure it's public. And here we're going to want to use our re-entrancy contracts that we've created. First thing that we're going to do is call the donate method on it. We will specify like the value being the amounts that we've sort of set up, I think. And we're going to need, because donates expects some parameter, some arguments to be passed to it. So we pass the arguments that it's expecting, which is some address, and we want it to be the address of this contract. You can see that donate is expecting some address up there. So we put that into our call to that particular function, having specified the amount that goes along with it because it's expecting some message.value. Once we've done that, I wonder, I mean, like, it's a bit risky for me to try with this 1000 way, but let's see how it goes. The next thing that we're going to want to do, as I say, is sort of, again, target our re-entrancy contract and this time call the withdraw function. And again, we're just going to withdraw our amounts, right? There's nothing malicious about that. We're donating and withdrawing. Nothing sort of too terrible going on, apart from, at the moment, us just needlessly wasting a lot of gas. But this is where the magic happens, right? In our fallback function, which we'll call, which we'll make external and payable. Because this is what's going to be triggered by withdraw in re-entrancy. And this is where we can begin to think about how it is that we could attack re-entrancy. I tend to prefer sort of think in if statements. So if basically, like, if the balance of the re-entrancy contract is not 0, we want to continually call it until it is, right? That's basically all the code that we need in here. We just need something that checks constantly what the balance of that re-entrancy contract is. And if it's not 0, it's just continually going to call withdraw and never allow it to get to the place where it resets the balances mapping associated with our address to 0. So it just continually calls withdraw, 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 withdraw until there's nothing left in the contract. So if we call the address of the re-entrancy contract and look at the balance of it and say that it's not equal to 0, then we're going to want to do some stuff, right? Which is going to be re-entrancy contracts, withdraw amounts. Okay. And this actually, that's, now I remember why I set this to 1 ether, because it just, if we set that to 1,000, it's going to take a long time. And with that number of calls, we'll probably run out of gas. So because I know that the balance of that re-entrancy contract at the moment is 1 ether, then I can do this without worrying too much about gas. We'll see, considering that we ran out of gas in our last endeavor. Let's see where we end up on this front. Yeah, that should do it as far as I can see. Let's see if it compiles. It does. Wonderful. Again, we get the same warning about having a fallback function but no receive ether function, which 0.8.7 doesn't like. But it's not critical and not particularly relevant to this function. As a general rule, I strongly suggest that you attend to all warnings in compiler, in your compiler, if you can. When you're writing like actual production contracts and this kind of stuff, these things are well worth paying attention to. For this particular context, it's not incredibly relevant. But yeah, we've compiled it. We will need to seed it again, Paula, with 1 ether, because that's what we're kind of expecting to be able to send, withdraw, and then re-enter on. And that should be reflected in our MetaMask details. Wonderful, wonderful, wonderful. I happily, just throwing ETH left, right, and center. We've deployed the contracts, perfect. So we've got all of our previous attempts to attack the king, which were disastrous. Let's see if attacking our re-entrancy works better. It looks about right. Let's confirm. Let's see what happens. The transaction was successful. Let's take a look at our balance. That's fine. I wonder, let's see. We can, to look at the balance of this contract, I think we can use Web3 get balance of this contract, this instance address, 0. Oh my goodness. There we go. It turns out that it actually worked. Incredible. I probably should have also like written a function in here to be able to like withdraw the ETH again, because you can see if I just copy the address of this re-entrancy contract and put that in instead of the instance, it should now have 2, I guess. Yeah, there you go, 2 ETH, which I could withdraw and send back to Paolo if I was, as I say, not feeling incredibly profligate today, which clearly I am. So yeah, you could write an extra function in here which just returns the funds to whoever calls it, which I should have done before deploying it, but alas, I didn't. So there's another 2 ETH locked forever on Rinkeby. So sorry, Paolo. I'm gonna have to, I don't know, make up for this in some way after our session today. So yeah, we should be able to submit our instance. Let's just double check and not believe me by just inspecting the balance of this stuff. And hopefully we'll be able to get a tick next to There we go. Nyan Cat doing his thing through the terminal. You can see that transfer and send are no longer recommended solution as they break contracts after the Istanbul hard fork. And sort of just as a way of like speaking about this intuition of like the language of defense, just always assume that the receiver of funds is another contract, not just a regular address, because then you're actively thinking about, oh, okay, what kind of logic can be implemented by this other contract on receiving funds, as opposed to just kind of landing somewhere and then being there forever. Yeah, and as they say, it's a common attack. It's not just what happened with the Dow. It's happened many, many times, precisely because of like what I tried to sort of like illustrate by saying that this is like like in the way that we have been conditioned over the last 400 years, this is a sort of indelibly logical pattern, right? You would check, you would then like do the thing and then record its effects. But as I say, like it's checks, effects, interactions, validation, optimistic accounting, actual events. And if you just remember, optimistic accounting, that'll be enough from this particular session with me, I think. Because okay, it's a nice bend, I mean, instead of all of these stuffy beanies at like the IMF and all of these other terrible places, you just have all of these optimistic accountants working on a shared ledger from their bedrooms. Interesting cultural phenomenon, if nothing else. Because I was kind of struggling so much with Re-Entrancy and King earlier, and as you can see, still have not got King to work. I haven't actually prepared the rest of the sessions, but that's kind of wonderful because it allows me to point you to what we're sort of working off, which is the Ethernaut's full write-up. So I'm just going to close the rest of the stuff and point to you. I will share this link in the Slack channel afterwards because there are a few, like CoinMonks did a series of write-ups with the solutions for all of the Ethernaut stuff at a particular time. Fluffy Pillow has done one. There's another one. I'm not sure that I have it up there. Yeah, I'll send you another one which is quite well done. Holly is writing tests for these things, so this has been done across the ecosystem, and you can use this to continue going through the rest of the levels, because this is probably going to be our last guild session. Certainly next week I'm traveling, but if you're sort of interested in exploring this more yourself, you can find a lot of the answers over here, which is what I've been working off because I'm a lazy developer. And as I said at the beginning of these guild sessions, developers are really just the people who have the grit and determination to continually bash their head against red stack traces until they figure it out, and who know what keywords to search for so that they can find the right Stack Overflow question and copy and paste the code that they need into their project. Of course, there are other aspects sometimes involved as well, like creativity and ingenuity and a certain kind of appreciation for language. But mostly it's just Stack Overflow, honestly. Anyway, so we can take a look together at this kind of setup for the next one, which is Elevator. And as you can see, the idea is to try and write an attack contract which will make this contract believe that we are at the top floor. And if we look at this, there is some kind of interface to a building contract which just has one function, is last floor, which returns either true or false. And then in our elevator contracts, we have a Boolean for like the top floor, clearly true or false, some unsigned integer for the floor that we're currently on, and then just one function, go to. And we pass this a parameter called floor, it instantiates like an instance of the building interface with the message sender, so our address, and then it has this if statements, which is, you can see that even the dev writing Fluffy Pillow like found it a little bit difficult to understand the exact logical flow of this contract, but saying like if it's not if this boolean is false, then set the floor to whatever was passed in, and the top is set to this boiling floor. So we can kind of take a look at, let's just, for some reason when I'm recording with Zoom, it just makes it difficult. So we can take a look and see if we can like unpack the logic of this contract and what's going on in real time based on Fluffy Pillow's delightful write-up. And as you can see, like once, we're going to write an attacker contract, and once we call go to, our instance contract will call last floor, first evaluate if the floor number we've pushed to it with go to is not the top floor. So basically, like there's a loop going on here, right? And he's like, oh my God, like what the hell is going on here? I know what you're thinking. I've been there. We want to be able to try and modify the states, but like we kind of can't do that just from within this contract. Like it's continually going to like set this to the like is last floor, and then this line of the contract like causes some problems for us, right? And we're stuck in these logical loops, which he's sort of being able to talk about here, not in the most clear manner, but basically what he said is that if I can put some kind of other Boolean, which I kind of enjoy his approach here, saying, or her approach, and we don't know who Fluffy Pillow is. Let's go with her. I prefer that, in fact. So I really prefer her approach here because they put a penthouse button sort of Boolean into the constructor with the value false. And then when they call go to, the instance, our instance contract, what he calls the target contract, will evaluate whichever floor number we've given to it with our last floor function, changing the penthouse button to true and returning false, which is what we actually need. Because like when the function is called the subsequent time, it will return true, which is what we need to pass the level. Like when Ethernaut, when we submit this instance, Ethernaut is going to check if this top Boolean is set to true. And so like if we put something into our constructor, which like has a double loop of true, which is set to true, then gets set to false. When we make our call, it will be set back to true when the check call comes through. So it's like a little bit difficult, I know, to follow those logical loops. But happily, we can kind of like step through the code ourselves and then see if we can satisfy one another that this is indeed what is going on. And this is what I've been doing for like each one of the tutorials that we've been going through. There's nothing kind of like magical about what we've been doing. It's just me like sitting here taking the time thinking about, okay, like how does this stuff actually work? I know that lots of other people who are far more intelligent than me have had a go at cracking these kinds of things, and if we look at their approach, we can learn a lot. And in fact, we can learn a lot by looking at a number of different approaches. As I say, like the Fluffy Pillow write-up, which I think is probably the clearest, and it's all like coherently in one place, which I dig, is probably the best. But Coin Monks have a whole series of them, which you can see is like happily loaded into my browser history. This one is actually not, but here we go. Each level is its own entire Medium post written by Nicole, who's really awesome. Hello, Nicole, if you ever watch this, thank you so much for your amazing work. Way back in 2018. So like this is a little bit older, but like it's got some wonderful graphics that, for instance, this is what we were looking at when we were doing the delegation tutorial, to try and understand how contracts can modify state from within the context of another contract. And there was another one, which I'll find for you. It's not loaded in my Brave history, but I'll also, there's, Holly will probably enjoy this one because there's like a whole bunch of the attack contracts and JavaScript written, and you know, it's quite clear, I thought. Anyway, we have, now that I've revealed the secret of where we get this stuff from, we can take a look at Fluffy Pillow's solution. You can see what we've sort of, the same kind of pattern that we've been using the whole time, which is something that I really like in terms of its clarity about like declaring where the address is, then declaring an interface across that address. As he says, as she says, there is this private Boolean declared and set to false when we deploy our attack contract. And then we write our own isLastFloor function, right? Which if we haven't pressed the penthouse button, then sets this penthouse button thing to true and return false, otherwise return true. And so then we can call this like pawn function, which operates on the elevator contracts, which is going to have this goto method. We can call any number that we like in the goto method. And how is that going to affect? I think we've got this isLastFloor, so that's clearly what's going on here, right? That's we've written the logic for our isLastFloor thing, such that the context from which this call takes place will always make sure that the penthouse, that the isLastFloor call always returns true. Yeah, I haven't explained that particularly well. If there's anybody else on the call, Holly or Paolo, if you would like to have a go at explaining why writing the logic for our isLastFloor function, which is only implemented as an interface here, will, you know, be sure to always return us something that is true. I'd be happy to hear it. But if not, and do feel free to interrupt me. Like, as you can see, like, again, just thinking about this stuff, like logically, like we're always going to want to have this call to isLastFloor return some Boolean that is true, right? And what's going on here is it's setting the top of the isLastFloor to, so it's saying like, it's constantly like saying that the top is going to be above what we call, I think, right? Yeah, because we have to call the isLastFloor with this function, with an unsigned integer, and we are expecting some Boolean return. And what Fluffy Pillow has done here is implemented the logic for our isLastFloor function and made sure that it will always return true. And if it's not like the penthouse button, then we set the penthouse button to true, and that returns false. So that's, we can be sure that we have called the isLastFloor. Yeah, it's really convoluted, the logic here, and I struggle to like put it into exact and clear English words for why it is that this will work. I can see that it will, but as I say, like the best that I can do on the fly here is to say that like we just want to implement the logic for this interface such that it always returns true.
It's just trying to go up every floor. The higher it goes, the closer it gets to that final condition, which is true. If it's on any other floor, it will be false. So yeah, Fluffy Pillow's implementation is acting like the up button on the elevator. Go up one floor, go up one floor.
There you go. Thank you, Sid. I don't know what we'd do without you, man. So we can grab this. I will, before I do that, just drop this into the chats if you want this. Sylvia, I'm so happy you found the about section. Oh man, it's really funny. It kind of ties in, I'm talking about like optimistic accounting, this kind of stuff. Like, like this is, it's so much of like where like cultural production actually happens, right? Oh man, there's so much to say about that. But we're probably gonna have a little bit of time, so we can go and look at that about section in our recording in a moment. So let's just, as I say, make an attack. So wonderful. Just put in a SVDX. Wonderful. So as Sid said, yeah, like it's just gonna like continually go up one and one and one and one. Like the up button on the elevator, we can get a new instance here. Use Fluffy Pillow's code and feel like we've really conquered Ethernauts. As I say, like I'm not completely happy with my own explanation of that, and I apologize for being like a little bit more sloppy than usual. But I can blame the king. It beat me today badly. I'm no king. I'm just the court jester, and as such, spent hours trying to beat it, but alas. So yeah, that should do what we need to. Again, we can compile it. It seems to work perfectly well, which is wonderful and surprising. In my own development experience, I think it's probably different for people like Fluffy Pillow. And seeing as it's all compiled, we're on Rinkeby with the right accounts, wonderful. We've still got some of Paolo's ETH. And there we go. We can deploy this particular contract. Perfect. Should be able to attack the elevator by just calling pawn. Let's see. If this works, the demo cards are, they've really changed their tune. I didn't even, look at this, let alone test it before our final guild session. So we've had a go. Let's see if we submit our instance with code not ours. Let's see if we can cascade our Nyan cats through the terminal and go and have a look at Fluffy Pillow's about section, because that's really the crowning achievements of today's guild. It definitely works, which is incredible, particularly given that I couldn't explain the logic even as well as Sid could. So thank you very much, Sid. I think that's like an absolutely spot on.
Yeah, I mean, I'll revise the logic a bit. It's not about going up. It's more like a switch. Like if the value of penthouse floor is anything other than true, it will turn it to true. So it will always take us to the final floor. So Fluffy Pillow is trying to ensure that whatever the value is, it will always take us to the final floor.
There you go. Even better. And now, because Sylvia has so kindly found out about the about section, if you if you join, it's really, I don't want to put it up on screen because it's going to break my computer and cause problems with the recording. But if you join hashtag kernel-garden, which is a wonderful channel in kernel, and scroll up a little bit, you will see the single most incredible photo from a man called Abe Uccello, who is one of the KB3 fellows and a dear friend of mine. And he is a paddleboarder in Siena Keys in Florida, among many other things, but mostly paddleboarding. And one time, a massive, like the most ridiculously big octopus, like just rocked up onto his board. He said like the hammerheads were kind of feeding below him in a channel, which is terrifying as it is. And this octopus just like came and chilled on his board, and he has a photo of it. So go and take a look at that if you're interested in these kinds of things. I am often, like, well, not often, but have been lucky enough to hang out with some octopi in the rock pools just down the beach here. And of course, you know, if you're looking for other crazy South Africans who enjoy time with octopuses or octopi, there's a wonderful documentary called My Octopus Teacher, which is shot in South Africa by a South African. So we have a particular proclivity for these decentralized brains, multiple hearts. So it's just incredible creatures. So also very cool that he lives in Barcelona. All of the best people tend to be around that part of the world, and I have very, very fond memories of a great deal of time spent there, particularly in places like Sagrada Familia and some of the Gaudi architected homes, which are really just delightful in so many different ways. Sid, I see you have a comment about that before we end today.
Yeah, I mean, last time we were talking about cats. This time it's about octopi. So that's one reason why I like Git. The logo of Git is an octocat, which is a hybrid between an octopus and a cat.
Everything is connected. It's wonderful. Thank you so much. Thank you so much. Thank you so much.